In this session, I'll describe some details of the Tetracorder expert system. The Tetracorder expert system is located in a directory, and here's one example. So we put them in T1 Tetracorder commands, and then there's a subdirectory for which version. And both these windows are in the same location. So in the directory, there's some README files, command.lib setup, that's the expert system, and the commands.start. Commands.start contains user changeable things on a image cube by image cube basis. For example, the deleted points, which library set, small number of channels, medium and large number of channels, and then the image cube and which command library, that's the expert system, which expert system to choose the image cube file name and the offset and scale factors. So generally those are changed automatically during setup, but you can also change them by hand. So I'll exit this. Then the other, you notice there are command.lib setup. There's not features, we'll get into what those are, and then different versions. What version is called is done by this setup program. And that's basically pointed to by, if you change the directory, you change this line, and if you change which command file to use, you'd change these, all of these in this directory. So that's the actual library. And so we're going to edit the library, and you see over here, D6 is the latest. I've made a backup in case I mess this up. Now the strategy here is if we make changes to this file, that means if somebody did another run or the same run on the same data set that they did a week ago, they'd get a different answer. So if there's a change to the command file that changes output, we no longer use the same name, we'll increment this. So typically we're running Tetracorder 5.2 and you change to like D7. If you make major changes, then we increment the letter here and go to E. So it'd go 5.2 D7, then a major change, 5.2 E1, and so on. So and during the course here, we will make changes and increment this. But in this session, I'm just going to describe characteristics of the expert system. So, oops, we already had VI set up there. Okay, so to begin with, and on a Linux machine running VI with the VI syntax in place, it color codes the output. So comments are in light blue here, cyan. These are the SpecPR free format IO routines are used to parse this file. So in SpecPR, a \# sign is a comment. If the \# is the first two characters on a line, that line is completely ignored. If it's not the first two characters on a line, it'll parse that line looking for commands to execute. So if we go down, generally we keep notes on changes that have been done. You'll see dates here, 2000, 2001, so on. Then we have aliases that must be defined in order for the command file to work. And if you noticed before in the start file, there were a lot of things defined there, so we can bring that up again. Anywhere where there's an equal brackets, those are variables that are defined. We do have some of those here. For example, this one, that's a variable that is assigned. You can read through this file and get the details. Because of SpecPR and the way the SpecPR file format is a fixed length record, and so a small spectrum will take up fewer records than a large spectrum. So we've binned the places where spectra go into 3 different sizes. So small spectra are 1 to 2171 channels, medium are 2172 to 4852 channels, and large, anything larger than that, up to the limit of SpecPR and how it's defined, which I for the current version that I'm running here, I think is 65,000 points. Now, imaging spectrometer data sets, I've never seen one that goes over the 2171 channels. Usually imaging spectrometer data sets are in the several hundred at most channels. AVRIS data that we've looked at so far in this series was only 224 channels. Some things have yet to be defined, like we don't have any spectral libraries convolved to more than 2172 channels. So if you need to go there, we'll probably have to do some checking of code to make sure the convolutions work right. But in 30 years of this effort, we've not had to go over that 2171 limit. There are knots defined, and we'll get into what a knot feature is. And the less than sign means read from this file, the command.lib setup knots ratios. And a different one is set up depending on what the number of channels are. Let me go down to an actual entry. Here's group 0. So from group 0 to the end action statement is the setup for one reference spectrum. So we can, the group number defines what group, which is basically a spectral range that gets assigned. Group 0 is a special case of groups that I'll describe later. This is use. Yes, you can change this to no if you don't want it to be used, which means you would hand edit this expert system file in your directory where you're going to do a Tetracorder run. In this case, we're expecting the data to be in reflectance. We had an option early on where we would convolve on the fly, but we've never fully implemented this because we've always found that you need to compare your data to spectral libraries once you start extracting spectra and verifying that the Tetracorder run gave answers that are quality answers and not messed up by some calibration artifact, for example, or you're testing something new and a new spectral feature, you want to be sure it maps correctly, that you define the continua correctly. So you need reference spectra to compare to. So if we convolved on the fly, we wouldn't have those. So right now, we're not using this line. It'll always be no, and we convolve the spectral libraries separately, so they're always there. The theory was on an imaging spectrometer that had variable wavelengths with different pixels across the scene. This is normally called spectral smile. Um, we could do that on the fly based on some other parameters that would define what the wavelength set was, but we've not had to implement that. Fortunately, modern imaging spectrometers do very well, and we can pre-process the data to be all the same wavelengths. Pre-ratio is sometimes used, and I can show examples of that. There's pre-processing is sometimes used, and we can discuss that in class. Algorithm, most of the time we're using the tricorder primary algorithm. We have a ID that needs to be a unique identification number or string. So this vegetation 1 shouldn't be used for any other entry in the expert system. And notice we have 25,000 lines of entries here. So there's quite a few different entries, many hundred. This section defines the reference spectra, and you'll see that we've only defined it for the small, and that's because we haven't been convolving for medium and large spectra yet. In the output titles for spectra that say single spectra mode, we have an output title that's somewhat redundant with this. You'll find elsewhere that we use the same name here as opposed to the output file name for images in an imaging spectrometer dataset. Our strategy is changing, so maybe these two should be the same, and so they're redundant. The main feature or the main guts of the algorithm is in two sections: the defined features and defined constraints. Features are spectral features. So this is spectral feature 1, and A here is, I didn't, in library records, we can also have an A or a B, and we could define a second set in case we want to mix the origin of the spectra. So this is coming from Spectral Library 06, convolved library record 7170. If we had, let's say this was a visible near IR spectrum, and we wanted to include a spectral feature that was in a different wavelength region measured with an FTIR, we could define a B library record and a different, it could be a SPLib06 or a different spectral library and a different record number, and then you'd have A's and B's here. So feature 1, feature 2, feature 3. Then we have what type of feature it is. D is for diagnostic. We also have optional and weak. Optional means that if it's present, and I better make sure it's been a while, corporate history is fading. We'll go up to the top and define clearly what diagnostic, optional, and weak are. The L is for linear continuum. We can also do a curved continuum. And then the W here is for the following numbers are in wavelengths in microns. We always use microns. So this particular feature has a right continuum from 0.522 to 0.552 microns, and that's the left continuum interval, and then the right continuum interval from 0.737 to 0.767. We generally try and do about 0.03 micron interval, because for the typical imaging spectrometer data sets, whether it's CRISM on Mars or AVERIS on the Earth or some other imaging spectrometers, it works out to be a reasonable width. So you get several spectral channels to average to get the continuum position intensity more accurately than using a single channel. Then CT is continuum threshold, and this is right continuum divided by left continuum threshold, and there are two numbers here, 0.9 to 1.1. So if the let's do continuum. Well, let's look at this continuum threshold. So there's one number here. So this is a hard cut threshold. If the continuum threshold, and this is the continuum at the band center where of this defined continuum. The band center is in the continuum removed spectrum of the reference spectrum, what the minimum position is. So it's not necessarily the midway point between the two continua. It's wherever the band bottom is. So the continuum threshold in this case is 0.1. So if the continuum is above 0.1, the fit is untouched. The fit is the correlation coefficient to the modified least squares fitting that's used in the tricorder primary fitting algorithm. If the fit is below 0.1, if the continuum threshold is below 0.1, the fit is set to 0. If you use two numbers here, like over here, if in this case it's the right over left continuum, if the fit is below 0.9, it's in this ratio, the fit value is set to 0. If it's above 0.1 or 1.1, the fit is not modified. If it's anywhere in between, it's linearly reduced by the distance from 0.9 to 1.1. So if the ratio was 1.0, that's halfway in between, so the fit would be reduced by 0.5. This interval we call fuzzy logic. If we let's mark this position. I can do that in VI. I set a mark here, and we're going to go up to the beginning of the file and search for. I'm searching down here. So this continuum threshold is a single value. It's a hard cut. Notice some of these other definitions are fuzzy logic. Okay, so let's go back to our position here. So that's all the parameters needed for one band. You can continue this on multiple lines if you don't have enough space. Lines for SpecPR commanding need to be less than 80. So these two lines here give you the line count. So 80 is that right there. So be sure that you don't go over that limit, or you'll just lose that whatever's beyond column 80. Someday with some programming time we'll increase that limit. Okay, so feature 2 is also a linear diagnostic linear feature and just has a simple continuum threshold. Then once we have, if let's say that a continuum threshold didn't meet this one and it's a diagnostic feature, then the material is rejected. Let's go back up and do we have this defined in here? Okay, so diagnostic feature must be present. An optional feature is optionally present. If the feature is not detected, its fit and depth are set to 0 and the material can still be identified. If it's a weak feature, but the area is set to 0, noise can mask a weak band, reducing the detection when a strong band is present. So use this only when necessary. We generally only use diagnostic and optional. And this is an advanced concept that we'll get into if the option comes up when we uh, do some more sophisticated commanding. Sometimes the weak feature works well, and other times it doesn't work. And so we found through a lot of experiment that the DNO are the two things to use. So if a feature is marked optional, let's go back to here. Let's say this feature was an optional and it didn't meet the continuum threshold, so it wasn't found. Then we could still find this material because only a diagnostic not found rejects the material. In this case, well, let me explain group 0. Group 0 is applied to most of the other groups as a way to, for the Earth, if there's too much vegetation present, it's difficult to see underlying mineralogy, so we don't try and find mineralogy. So these are pretty well hard cut, so that once we get enough vegetation and we've experimented with the level that this shows, that we don't try to find the other things. But you'll see that we can still detect pretty good mineralogy in the presence of some vegetation, and we saw that in the case when we mapped at cuprite. So once the individual spectral features are found, then global constraints are applied. And here is the temperature has to be between, well, we really haven't constrained this down. This is basically any temperature that's plausible can still find vegetation, or basically a chlorophyll band. And think about it, you can have a vegetation that's frozen solid, and chlorophyll will still show the absorption. So green vegetation up in the Arctic will still look green and show the chlorophyll spectral feature. Pressure, we really don't have any constraints on pressure here, so this is something we could choose, and we probably ought to bring that temperature down some. Then and notice there are 4 numbers here, so this is fuzzy logic again. So vegetation wouldn't be rejected by this, not at the lower limit, and it'd have to be above 600 Kelvin, which is probably have the vegetation on fire. Same with the pressure. We have 4 numbers, so we have fuzzy logic minimum and fuzzy logic maximum. Then the other constraint, that looking at the fits, once these 3 features are found, the fits for each of them are combined into a weighted fit, and the fits here would be checked against that. So again, fuzzy logic. So the fits have to be basically greater than 0.6 in order to be be accepted, and if it's below 0.6, it starts getting reduced, and if the fits are below 0.4, then this one is rejected and not found. Same with depths. We're only rejecting this if the vegetation is too thick. So we've set the band depth from 0.5 to 0.6, and that's indicating a lot of vegetation in the pixel. Okay, then we go down to the output. The output is saying output all three, the fit, the depth, and the fit times depth. And these are weighted based on the number of features and the areas of each feature in the reference spectra. The output file name will be vegetation1.fit, vegetation1.depth, and vegetation1.fit times depth. The depth will be scaled to as an 8-bit image, where the maximum DN of 255 would be 1.0. So the minimum depth that could be detected in the output image, of course, we've thresholded it. If this threshold wasn't there, it would be 1 over 255, and below that it would just be 0. You'll see below, when we get into minerals, that often this value is set to 1, so then we're have a lower intensity range for the depth of 1 over 1050. The output files are compressed with a gzip compressor. There are other actions that we can do, and we'll go find some other example actions. So if we're in a single spectrum mode, a sound file will be played to give you the answer as an audio clip. And then there are no other actions. There can be multiple actions here. So let's go down. Most of these will be similar. Here's a vegetation mixture, and there's a lot of, we're looking at 5 spectral features. Let's go down to group 1. We should discuss what the different groups are. So let me, I'm going to mark this position, and we're going to go up to the top and find the group definitions. Okay. Turn that highlighting off. Okay, so group 0, like we had already discussed, are a catch-all for other groups. Group 0 is always included in all the other groups unless there's a specific definition of, say, don't include this group. So group 1 is electronic absorptions, nominally in the visible and 1 micron region. Group 2 are vibrational, narrower bands that are typically in the 2 to 2.5 micron region. Now, all of these groups can use any feature they need to make an identification in any wavelength range. So, for example, in the 2 micron group, we're often using, for example, Aliases, we're using features in the 2.2 to 2.3 region, plus a feature in the 1.5 micron region. Group 3 is vegetation detection. Now that's different than this group. So group 0 is applied to group 1, group 2, and so on. Vegetation detection is just trying to find any trace amount of vegetation in a spectrum along with the mineralogy. And we saw that at cuprite in the cuprite example. Group 4 is broad absorptions in the 1.5 micron region. This, and 1.5 is a loose range, so it includes Fe2 plus in feldspars. It includes olivine, which is a little bit longer wavelength than the typical pyroxene bands at 0.9 microns. Group 5 is broad absorptions in the 2 micron region. This includes pyroxenes, broad pyroxene bands that are between typically 1.9 to 2.3 microns. And then we keep going out into other wavelength regions. Things in the 2.5 micron region, the OH features in the 2.7 to 3 micron region, another group, narrow bands out there. Group 9 isn't used. We'll probably add some stuff in the short plus micron region. Groups, let's look at these two. So we have two 3.5 micron regions. One of the things that we have in typical reflectance spectra is there's a lot of curvature in the 3 micron region due to coming out of the typically present water band near 3 microns. So at 3.5 microns with a linear continuum here, we would have false positives mapping trace organics. So this is using curve continuum for the same features that are in group 11, but have better chance of detecting trace organics. And this looks like it's doing very well. We need to add more organics to group 10. 4 micron region in group 12. Then we have groups 13, 14, and 15 are narrow absorptions in the 1.3, 1.4, and 1.5 micron region. This needs to have more entries put in. There's quite a few in there now, but if we want to make this fully diagnostic, we need more entries because there are many minerals that have absorptions in this region. Group 16 is not used. Group 17 is a 1.7 micron region. It needs entries. Group 18 is not used. You might detect a series here. 13 is for 1.3 bands, 14, 1.4 bands, 17, 1.7 bands, and so on. So 18 nominally would put in 1.8 micron features for things that have absorptions there. 1.7 has both CH and water bands, so that could be a good diagnostic region. 1.9 is 1.9 micron water bands and ice, and this is generally shows trends, but not ironclad specific mineralogy, except ice is quite unique. Searching for rare earth oxides is important. There are rare earth oxides in groups 1 and 2. So, but this does a deeper search for trace rare earth oxides in these three. So if you ever see something mapping here, because we're mapping at a lower level, it could be mapping on noise or calibration artifacts. So you need to verify any of these by extracting spectra and confirming they're really there. So like we discussed in the group 0, an action can call something, and often we do a special case. So here's if we detect vegetation, we do a red edge shift, and if we also detect vegetation, we can do a spectral type, and we can go and check some of these where these things are being found. Then we do special cases to get the water band depths for the 0.9, 1.2, and 1.4 micron band depths. And there's a special case for if we find epidote or chlorite or calcite to do a mixture series. Case 7 is, and for example, this mixture series was constructed by Brad Dalton, and he wrote a paper on this. Case 7 is looking at carbonate, where we use more diagnostic features to be sure of the carbonate identification. Let's do a quick search for entries that do case 1. So here's a case, and this is group 3. And if you remember, group 3 was vegetation. So it's a vegetation map. You can see that right here. And if you detect vegetation, do all these cases. And remember, case 3, 4, and 5 were the 0.9, 1.2, and 1.5 micron water band depth. So that's an example where a case is called. So there are many, many strategies that could be done. We've through this command file, you'll see one strategy from mainly the work of myself and colleagues at the USGS. And this is not necessarily the only strategy. We could come up with completely different strategies, but there's a dozen or so expert spectroscopists have worked on this expert system with many, many years of effort. So we think it's pretty good, and the mapping results so far have been really quite robust. So let's go back to group 1. Okay, so this is begin group 1. So group 1 doesn't, well, this is an odd one, but a plastic tarp showing a green absorption band. Let's go down to where we have some minerals. Okay, so here's a medium grain goethite. We're mapping on 2 spectral features. Pretty standard constraints. We've made these a variable in case as imaging spectrometers improve in signal to noise, we might be able to lower these thresholds, because as you go down in reflectance level, your signal to noise for defining a spectral feature depth is decreasing. But as systems get better, we might want to adjust these values. Let's go to group 2. And let's go down to a mineral. This is dry grass. We want to get to some minerals. In fact, I want to go to a Montmorillonite. Do I have to type correctly? Okay. So this is a sodium Montmorillonite, where we have only one spectral feature, and we have knot. We have 2 different knots. We have a knot gypsum and a knot muscovite. So Montmorillonite is a very simple spectrum with one spectral feature in the 2 to 2.5 micron region, but that feature is almost an identical match to a feature due to both of these are due to an aluminum OH stretch bend combination, and the muscovite has a very similar, very, very close spectral position, shape, width, everything. But muscovite has additional features in the same wavelength region, and so does gypsum. So in this case, we're looking for this not muscovite, and because it's in brackets, this is a variable that's defined above which one it is, and we're looking at spectral feature 2 from this muscovite, and the band depth needs to be greater than 0.15 times R1. So let's go find this spectrum. We'll mark this position. This is, got to find where. This should be the definition. So it's not in here. It must be, oh, it's in the knots. Okay, so this is the definition of the knot spectral feature. So it's spectral library 06, record 3388. So if we search for that, oh, actually that will be over here. Okay, so we need to get to group 2, not group 8. Okay, so we're in group 2, muscovite, medium high aluminum, and spectral feature 1 is the 2.2 feature. This is the other, so this feature is almost identical to the Montmorillonite feature, but muscovite has a second feature that's at a slightly longer wavelength, and it's always a fraction of the strength of feature 1. So that's why in this Montmorillonite it has to be, if a feature greater than 15% of this strength occurs as feature 2 from this Montmorillonite definition, then this gets rejected as Montmorillonite, and it would probably be found as muscovite. And similar with a gypsum. So you see, it can get pretty complex. So you have to understand the intricacies of what makes a diagnostic absorption to make an identification of a material. So there are basically hundreds of materials that are defined in group 2 and potentially hundreds in each group. So what happens when Tetracorder goes through all these feature definitions, knots, constraints, all of those impact whether or not that feature is plausibly there. Let's say 10 different minerals were plausibly there, that they weren't zeroed out by one of the constraints, and features existed that gave a fit above the thresholds. Then what happens is those fits are compared, and the best fit is chosen. Now, sometimes we've had strategies where, well, should we also put out the second best fit? And there's a Swayze et al. 2003 signal to noise paper, which I'll send out the references for, but it's JGR 2003, Swayze et al., and then the Clark et al. 2000 JGR paper for the Tetracorder description paper. The studies there showed the algorithm's doing very, very well, and we haven't found a need to do the second one. There's so much to analyze already in the output that doubling that would add a lot of complication and assessment. And so far, in our assessment of how these identifications are being done, the current strategy is working very well. So we need to continue with that, and we do testing on known sites. So if you have for example, you have a site that the composition of, you've worked in the field, collected samples, know the mineral composition, and there is an imaging spectroscopy data set over it, you could use that as a test case when you make additions to make sure that the mapping is still consistent with what you know from being on the ground. And we have 4 such test sites. Cooperite, Nevada is flown often by JPL as a good test location. We also have, so that's a hydrothermal system area. Then we have Joshua Tree National Park, Arches National Park, and a line over the western Denver metro area. And we've done extensive field work in these locations. So, and Joshua Tree is a metamorphic environment. Arches is a sedimentary environment, and then the western metro area is a city environment, which would have very different materials. So with that, I think we've covered the basics. You can, I encourage you to page through the expert system, read this beginning section. There will be here's the discussion of the continua and the diagnostic and optional and weak bands. Here's a discussion of the fuzzy logic and other details that will help you understand the strategy that's used and the commanding that is used. Let's make sure this I didn't accidentally change something there. It still has an October date. That was the last time something was changed in this file. So yeah, I didn't mess something up. Always check that. If you do make additions on your own system, then you can increment this number, but also send us the information that you've changed so that we can work together to grow the system to do more and more things with more and more diverse environments, and we'll keep propagating this expert system to do a better job. Thank you for listening.